Hello Internet! In this video I wanted to take a look at Boids, and I'm hoping we can implement this in Unity by the end of this video. This is all I know about them, other than seeing them used in a few other places. So this could go in a number of directions. I'm hoping it goes in the correct direction and we get this done. But there are three rules with Boids. I was meant to refresh this because there's actually an example in this page, which is why I wanted to start here. And so the idea is Boids try to fly towards the center of mass of neighboring Boids. And so in this case, a Boid is like a virtual bird. It's simulating some sort of like very basic life thing. And so you can see these arrows kind of flying around and how they're kind of grouping together. That's a Boid. That's what we're trying to do, except we're going to probably do this in 3D. I don't actually know if that's going to work, but we're going to try it and see what happens. And so the first thing is they're going to fly towards the center of mass of neighboring things. So effectively, there's going to be a radius around every Boid in the simulation, and every other Boid in that radius is going to be averaged, and we're going to try to reach the average point in that. And so that's going to be like our destination. They try to fly or try to keep a small distance away from other objects, so there's some sort of repulsion away, so they don't all just group one on top of another. Because again, they're trying to move towards that average, and so if there was no way to repel them, they would all just group one on top of the other, and you just get all the objects one on top of one another, and we don't want that. And then Boids try to match velocity with near Boids, which means again in that same circle, every object is going to be moving at a specific velocity, and so we want to average those velocities and then try to get to that average velocity. And so those are the goals, and we'll see how this works. So I'm assuming it's not really like that. That's all there is. There's this other paper or thing example from Stanford that does similar things. It's showing the same kind of thing. It has them separated into separation, alignment, and cohesion, but they're kind of the same thing. They're just in different orders. I'll link these later, but we're going to be using them as a reference to kind of build this whole thing. And I'm hoping each of these seem fairly easy, and we're going to try it in 3D because Unity is a 3D engine, and I think none of this math should depend too much on the dimensionality of it. So it should be the same whether we're working with 3D objects or 2D. We're just using vector 3s or vector 2s. That's the difference. And so hopefully that's it. And we'll see where this ends up going. So I'm gonna throw that over there, and we've got Unity up here. There's nothing here. So if we go into this Boids folder that I've created, I've just kind of been throwing everything into this project recently. Maybe not a great idea, but let's create. I guess there's three things that it's going to try to do, right? It's going to try to move towards the center of mass. It's going to try to match the velocity, and then it's going to try to move away from things. And so those all three are going to be modifying the velocity of the Boid itself. And so we can make this with 4 scripts. I think that's what I'm going to try to do. And that way, if we want to add additional behaviors on top of this, we can just add additional scripts. And so the first script is going to store the velocity that of the Boid and effectively store the brain of it. And then those other 3 scripts are going to implement each of those 3 rules independently, and they're going to operate on this original script. And so let's get that. And this should handle storing the velocity, and that's actually going to be a vector that's going to have a direction and a length. So we know how far and in what direction we want to move. And then it's actually going to handle that movement as well. And then everything else that just updates the velocity should hopefully cause this all to come together. So we'll just call it a Boid. Why not? That should be everything we need. And so we just need a vector 3. I'm not going to be using any physics here. We shouldn't need to do that. I don't think. So we'll see what happens, but I believe we can just work with basic basic vectors, and everything should work out. So this will be our velocity, and then with all velocities we want to just move in some direction. So we're just going to do this dot transform dot position plus equals velocity times the time delta. So if we have a velocity of say 10 in that direction, we're going to move 10 units every second effectively. And so ideally this velocity is going to be updated every frame, and we can figure out those equations later, but that's the general idea. We'll probably want some sort of randomization of all of these vectors. Otherwise we might get some weird behavior. But for now, I'm just going to leave this, and we'll probably leave that randomization up to some other script that's going to actually spawn these things in. So we'll probably write a fifth thing that's actually going to spawn a number of these Boids just as prefabs, and then set the velocity to random things. So they all end up kind of doing random things, and you get a different result every time. Right. So we have that. Let's create... I guess we'll just use cubes for this. And we will attach our Boid onto that. We can remove the box collider. It's not going to do anything in this. And so there's no real point to having it. And I'm going to shrink this down a little bit, down to like 0.2. And we're making these small because I want to have lots of them, because I feel like that's just cooler. And we should, I don't anticipate any big thing causing this to go really slowly. Wants us to save the scene. I'm going to do this just in case I lose anything, so we're just going to call it Boid. Sure. And we'll do just like move along the x-axis. So that should be this one. So we should see it move in this general direction, like off the screen in that way. It's different on both screens, but you get the idea. There we go. So we get this really slow movement along our x-axis, and that means that it's working. The only other thing I want to do is we're going to be modifying this velocity. And so what I want to do, just so we have a little bit of a better idea of where things are headed, I'm going to rotate this towards wherever it's moving. So we're going to take the quaternion dot look rotation. And so this allows us to give it just a specific forward vector. In this case, we can just give it the velocity. We could give it an up vector as well, but we can also just give it a single vector. This is less deterministic. It doesn't actually give you a exact result. You could because there's multiple ways. Like we can look in one direction and just get the z aligned with that direction, but we can rotate 360 degrees around the other thing. And so there's lots of different options for this to actually return. That's why the up is an option. But if we don't provide it, we should get something. And that's all we want. This is a visual thing. It's not going to impact anything else. And so I don't really care. Again, we're just working on the velocity here. We're not trying to simulate like realistic rotations and movements like that. So this isn't going to change anything. But if we increase our y, you can see it ends up turning in that direction. And if I go backwards, we'll probably way off the screen. There we go. But the cube is turning. That's all I'm trying to say. So this is, I guess, the basics of it. So all we need to do at this point is actually start implementing the effects. So the first one, we want to move towards the center of mass of other Boids. And so in order to get that to work, I'm going to add a few of these. Actually, we were talking about doing... I was thinking randomization, but I'm actually not going to do that yet. And the reason is I'm kind of concerned that I'm going to use the randomization in some way that I shouldn't. And it's going to make it really hard to have a deterministic thing. This way, if we run into an issue, we can make small changes and get the same results-ish. But if we actually try to reuse or do random stuff and run into problems, we can't reproduce that. There's no way to get back to that scenario that caused that problem. And so this way we get something that we can actually constantly keep retrying at and hopefully get a result. So if we start this, we should see all 5 of them just move off the screen like that in sort of a uniform direction. And that's pretty much everything we expect. And so let's do, what was it called? I believe it was Cohesion. So let's remove that behavior and create a new one called a Boid Cohesion behavior. I might have spelled that wrong. I have a reference right there, but I didn't look. So we're gonna go with this. Seems like it, but it doesn't know what Boid is. That's fine. I have a spell checker installed. That's what this underline is. It just helps with like comments and other things. In this case, it can get kind of annoying, but whatever. So these are all going to be kind of based on the same thing. It'd probably be a good candidate for like an abstraction thing, but we're not going to do that because these are small and that's just more work. And there's only 3 of them, so it just doesn't make a lot of sense. So I'm going to require a type of Boid, and we are going to say Boid equals get component of type Boid. And now Boid isn't defined, so we need to define it. And so we can just do not that. Whatever that was supposed to say. It was supposed to say this. There, finally got it. And so we're going to store the Boid and actually be able to operate on it in this update. And so what this is supposed to do is actually find other nearby objects and then figure out a target point near there. And so for that to work, we're going to need a radius because we're going to need to search for everything else in a specific radius. And now I'm not storing these in any intelligent way. There's no data structure behind here that is actually making this useful. If you want to do this in something realistic, don't do what I'm about to do because we're just going to find all objects. We're just going to go and actually like find all Boids. Yeah. Is this the right one? Yeah. So find objects of type Boid is just going to return an array of all the Boids in our scene. Problem with this is I'm going to be running this every frame for every Boid in my scene, and I'm probably going to be doing this in multiple components, which is slow. We can, again, we could have a data structure that tracks all the Boids in your scene, and even optimize it beyond that to make checking for local objects much faster. There's things like octrees that would make that possible. We're not doing that because those take more time and example stuff. So if you want to actually apply this in something you're doing, I would recommend looking into that. But again, we're skipping it. So we're going to get all of our Boids. This isn't going to include the current one. So it's going to include ourselves. So now that we have all of this, what we want to do is actually find everything inside of that radius. And so we're just going to do a vector 3. How do we want to do this? We can do the average and set it equal to a vector 3 of 0. And do found equals 0. And so what we're going to do is we're going to just sum up everything nearby us, and we're going to divide that by the number found. I think that makes sense. And we are actually going to do a difference here. So the average is not going to be like the actual real world positions. I don't think that's what we want. Instead, we're going to actually take a difference of that. And so in this case, for each var Boid in our Boids dot where I'm going to pull in link here and just pull out the Boid that is ourself, where the Boid, where B is not equal to Boid. And so this is just validating that we're not matching ourselves, because it actually isn't required, but it makes it a little bit easier. And if we ever want to do anything else with this calculation, we're avoiding the complication of having ourselves in there. Since we're just taking an average, it shouldn't impact it, I don't think, but we're gonna remove it. So if Boid dot, let's calculate the difference. So var difference equals our Boid transform position minus, that's going to be difficult, this dot transform dot position. And now that we've subtracted those positions, what we want to do is actually calculate a few things. So we're going to calculate the distance between them, and we have that through the magnitude of the vector. And so if this is less than our radius, we're inside the distance to add it to our average. So our average plus equals the difference, and then the found plus equals 1. So we're just saying we found one additional vector, and we're adding the difference between the two onto this. And then the normal of this difference is actually going to be the direction that we want to move in. And the length of that is going to be how far away that average is. So it could be very far away, in which case we want to probably move with more force, or it could be very close and we want to move with less. And so those are, I guess, the goals. And so for each blah, and then at the end, we just need our average equal to average divided by found. And we want to do that if the found number is greater than 0. So if we found any objects in here, then we want to do this. And then at that point, we have our average. And so we just need to move everything towards that average. And so in order to do that, we can do Boid.velocity equals something. I don't actually know what the correct thing for this is. We can try a lerp. That might be a little bit overkill, but it might work. I don't know the best way to do this. So we're going to guess velocity here. Do I want to use the velocity? Okay, so thinking about this a little bit more, we have two things, right? We have our Boid's velocity and we have the average. Now, what I'm doing here is I'm putting the Boid's velocity on the left side and the average on the right side, which means as we increase towards 1, we're going to move towards the average. And so as you get lower and closer to this velocity, it's going to become less and less powerful. And so what we can do, I'm thinking, is do Boid.velocity.length .magnitude, sorry. Or do we want to steer it? I guess that's the other option, right? We can actually steer the entire vector. And so instead of slowing down or increasing the speed of our Boid, we could actually modify the vector in some case. I'm going to do this because it makes sense. And I'm actually going to make this an addition here and make this the vector3.0. So there's no change if we're really close, and there's lots of change if we're very far. And the way we can do this is just divide it by the radius, because the radius should be the maximum distance. It should be the far end of this. And so if it's right on top of us, we should get 0 out of this average. What did I do? Average magnitude. We should get 0 out of that average. And then we'll divide it by something and get an even smaller number and do nothing. But if it's very large, if there's a very big difference, we will get a up to the radius in the change, and then we'll move towards that point. And so hopefully with this, we've modified our velocity and we should be good. This is also going to cause us to accelerate off into infinity. We probably don't want that, but I'm not going to limit the velocity here. I'm going to limit it here. And so we're going to do a clamp here of do if velocity dot magnitude is greater than max velocity, then we can do a velocity equals velocity dot normalized times the max velocity. And that's just going to clamp it effectively and pull it back down to whatever the max velocity is if it ever goes over. And that hopefully gives us a way to kind of prevent infinite acceleration, because that was what was going to happen. And so we have a few values to set at this point, but hopefully it should work. or maybe it won't. We'll, I guess, figure that out real quick. So I'm going to set the radius to 5. We could add a gizmo or something to make that a little bit easier to see, but we'll also set a max velocity of 2. And now if I did this right, they should all move towards one another and do that. Perfect. So now they're moving and kind of grouping among themselves, and they'll just keep going. We could actually probably change. Oops, that's the wrong way. Oh, I was modifying all of them. So if we just change one, I think, yeah, we'll get more interesting results by modifying the velocity of a single thing, because you can see I just changed the direction of the entire thing by only changing the velocity of one object. And so that's sort of the idea here. The only problem is they're like grouped onto one another, and they're kind of like orbiting instead of swarming, if that makes sense. So instead of like forming into like a flock of birds, it's more like a chaotic planet that is exploded and now just spinning out into something. And we don't really want exploded planets. So we're gonna make it not an exploded planet by doing the other 2 steps. And those are Boids try to match velocity with their nearby Boids. And that is called alignment. Let's try that. So let's create a Boid alignment behavior. I don't know if these are like the technical things. I just found this like site on Stanford's website and figured, sure, why not? That sounds like something that would be useful. So we're gonna explore that, and we'll see. But for the most part, their names are better than mine, so we're gonna use theirs. I think that's sort of the motivation there. We also need link in here. So I just copied everything from our cohesion behavior over here. And so we can just change this bottom bit, everything from here, to try to get something else. And so alignment, the idea is we want to, that's not the right thing. It's not called an alignment behavior. I screwed that up. Anyway, what this is going to do is it's going to match the velocity of everything nearby it. So in this case, we're taking the average, we're doing all of that, but we're using position here. We don't want to use position. Instead, we want to do Boid dot velocity, and do if the velocity. We don't need to do anything with the velocity. Why am I checking it against the radius? We don't need to do that. We still need this. That's the difference. Average is going to be the Boid dot velocity instead of anything else. And then if found is greater than 0, so if there's something nearby, we actually want to apply this function again. And so we're going to get back to our average and then try to match that average velocity. And so one of the ways that I like to do this is not correct, but it does typically work, is do something like vector or do Boid dot velocity, and then give it the average as the second parameter, and then just do a time dot delta time as the opposite, or as the form as the function of this. And so again, this is going to lerp from the velocity up to whatever the average is. So it may be higher, and so we'll draw a line here. And then the idea is you want to move towards this far point. But we're giving it time dot delta time, which is really small. So we're going to get just a little bit closer. And then the next frame, we're going to get just a little bit closer. And it's going to kind of just shift this further and further towards this point. And you get sort of like this smoothish curve. I don't think it's exactly like mathematically correct, but for like a majority of cases, it gets close enough. And so it kind of is a cheaty way to do this without having to get into a lot of more complicated math. At least math that I am not aware of how to do yet. And so we're not going to do that. But this should be everything we need, I think. We have our Boids, we calculate the average, and then we lerp towards a common velocity. And that should actually cohere and get everything to actually try to go in the same direction. And so hopefully those two play nicely together. And we can just attach that to all of these Boids like this, give it a radius of 5 to match the other one, and run it and see what happens. I'm lost. Where did they go? There they are. All right. Right, so we have a line now. And so they've matched their velocity. That's the point, I guess, of this. And so the only other problem we have is they're intersecting and grouping into one another. And we don't want that. And so what we want is some sort of repulsion force that's going to push them away. Sort of like an inverse gravity, or like two equal poles of a magnet being pushed close together. When they get close enough, they decide, no, this isn't good, and they go in the opposite direction. We want that, but for Boids. And so that's what we're going to make. And I am going to call this Boid inverse magnetism behavior. That's definitely not the right name, but we're going to go with it because I like the name. And that's as good a reason as any. And so we're just going to do pretty much the same thing. Yeah, okay. I thought I did something very wrong, but I didn't. So we should do that. And effectively, we're just copying everything, except I'm trying to not overwrite the class name because apparently this is easier. I don't know. And so what we want to do here is probably have a smaller radius and a public float repulsion force. I'm making all of this up as I go. I want to be very clear with that. Those documents I showed are there's no math on them anywhere. It's just those few lines, and that's pretty much all I'm basing all of this off of. And so just adding things that seem like they'll make sense, and we can kind of tweak it as we go. So that's where we're at. So we want to move away from anything near us. And so in this case, if the magnitude is less than the radius, we're too close. And so we want to move as far away as possible. And so we're going to average out all of this. And then if we found something, if something is too close, we need to add that force. So Boid.velocity is going to be minus equals. We're doing velocity here. I actually want to do Boid transform the diff, sorry. We can just take the diff and add that there. And so this is going to be a direction towards whatever it was, like we had in the last one. So if we look at our cohesion behavior, we're moving towards this. But we can actually copy that and do the opposite. So in this case, we're moving towards. We want to subtract by the repulsion force. So times what am I doing? Times the repulsion force. And that should be everything that we need, right? So again, same thing as pulling it towards everything, except in this case, goes away. and we just have a different radius and more force. And so hopefully that overrides the other one. And so effectively they're like multiple curves. One's going away and one going towards, or however you want to think of that. And eventually they're going to cross. And so when they cross, instead of being pulled towards that specific position, it's going to be pushed away again. And so that's how this is intended to work. Because we're not using physics, nothing's going to collide. It's not going to actually like hit anything. We could probably add like rigid bodies onto this. Instead of using velocity ourselves, we could use actual velocity of a rigid body and simulate this physically, but I'm not. So let's see here. If we grab this, attach our inverse magnetism. Let's say if they get within 1 radius, that should be fine. And we'll repulse with a force of 10. And so because this is a curve, it's just going to make this curve sharper or whatever. Let's decrease this a little bit to like 2. That actually doesn't look too bad. Now there's too many things going on. I don't know if that's right or not. 0.5. Okay, that seems better. So 0.5 and 1 was what we were using. So let's just keep that in mind. And I think everything should have not updated. I need to actually save this component. I forget how to do that. Apply all. There we go. And so now I've saved that Boid. And so now we get to have fun. we get to break things. So let's do a Boid spawner. And so what this Boid spawner is going to do is it is going to take a public game object of our prefab, which is going to be our Boid prefab, and then it's going to take a public float radius and a public int number and spawn that many things inside of this radius. And so what we're going to do is do for I while I equals 0, while I is less than number, something like this, just a basic for loop, and then instantiate our prefab at a specific position. And so for that, we're going to use this transform position plus a random inside the unit sphere. And now the unit sphere is just a sphere at 0, 0 that has a maximum radius or a maximum radius of 1. And so anything inside of that sphere is going to be a valid spawn location. And so if we multiply that by our radius, we will get a sphere effectively as big as we want it with random points all throughout it. And then for the rotation, we can just give it a random rotation. So we can just do quaternion or just random rotation, rotation. Done. And so for that to work, we are going to actually need Boid to set the velocity here. I said I wasn't going to do this, but actually this makes a little bit of sense to do velocity equals this transform dot forward, so the forward vector of the object, times the max velocity. And so we're just going to have them all start at their maximum speed in whatever direction they're intending to go, and they'll figure it out from there. Or we could just have it start at 0. That would be a possible too. I guess we can start there too and see what happens. I don't actually know. And so we'll see. But this should be enough to actually spawn everything, I think. Maybe I screwed something up and then this won't work. but I'm pretty sure I did this right. So if we attach our Boid, give it a radius of, let's say, 25, and let's spawn 100. This is going to be big, so we're going to back up. So let's give ourselves a little bit of room and run this and see how much we screwed up. And you can already see, I don't know if it's showing up in the recording, but my computer is chunking a little bit. At least Unity dropped a bunch of frames. And that's mostly because we're now doing hundreds of checks every frame for nearby objects. But you can see we've kind of got these clumps of objects forming as they get closer and closer, and now they're all flying away. And so what we can do, because this video clearly hasn't gone on long enough, we can limit all of that range. And so we can do a Boid container behavior, because there were those 3 behaviors that we wanted, but nothing says we can't add more. So that's what we're going to do. And so we can just, I guess we don't even really need all of this. We can just take this bit. And so we're just going to replace the start method and require this. So we're going to require the Boid again and just work on that. And then the radius, instead of keeping something or trying to pull something in or doing whatever, if you go outside of the radius, it's going to move you back towards 0, 0. And so how are we going to do that? We're going to do it the same way we did everything else. So this cohesion behavior, we're going to want something like this. But instead, we're going to do if Boid.transform.position is greater than the radius. So this is assuming that it is outside or centered at 0, 0. This won't work anywhere else, just because example, and it becomes a little bit more difficult with the math. We need to add some extra vector. And so we're just not going to do that. And so this is just going to take the position if it's outside of the radius, and we can test that by using the magnitude. This effectively creates a bubble around it, and if we get outside of that, then we're too far. And so we're going to do Boid.velocity plus equals vector3.lerp 0, and we're just going to try to move back towards the center. And so we can do that by doing radius. How do I want to do this? Radius minus the Boid transform position magnitude. And so if we do this, that's going to give us a negative value because the magnitude is greater than the radius. And so we're going to get some negative value, and it's going to increase as you get further and further outside. And then all we need to do is give it the direction from wherever we are to go back to that. And that's really easy too, because we already have that. We have this transform.position, and that's it. That's our vector. And so we just normalize that and multiply it by whatever this is. And we can do something like time.delta time, just to kind of smooth this out just a little bit. But that should hopefully push it back towards the center. And as long as we have this check, it should never push it back out. Because what this would do if we didn't have this check is get everything in a ring around the outside, and we don't want that. Instead, we want everything to kind of move towards the center. And so the idea is that hopefully this helps accomplish that. There's no extra force here, so there's no like multiplication, but we can actually adjust that too. So we can do public float boundary force. Again, making up values because we can. And so if we just multiply that on top, it'll just increase the scale of whatever we're doing. So as you get further and further outside, this boundary force is just going to get really big, either really fast or really slow, depending on what you want. You could even set radius to 0 and have a lower boundary force, and it would slowly pull everything back towards it, do some sort of like gravity thing. Theoretically, that would work. But again, making things up, so who knows? Let's see here. Do we have the container? We do. So let's give it a radius of 5, like I was saying, so something small, and then we'll just give it a really small, like a weak boundary force, like 0.5. And so hopefully that causes things to kind of stay together, and we get a little bit less scattering and then just flying off into nothing. So there is everything. And then hopefully everything will kind of collect, and it seems to be. And then as things get closer and closer, they'll move into one another even more. And it looks like this final group is following along and is going to get pulled in as well. And now we just have this big group of things moving around. And as they hit a wall, they should all turn, hopefully. It'll be a little bit slower because they're not actually, like, they'll have a stronger force going in the same direction because they have that attempting to all match the same velocity. So the more of them there are, the stronger they'll move to get outside of that boundary. But now we just have this giant conglomeration of things. Because we don't have enough force pushing things out, they're inside of one another. So we can actually change things in real time, because why not? Let's set that to 5. What happens? They all spread out a little bit more. We can increase that even further to like 10. Okay, that looks a little bit crazy, but you get the idea. And so you can kind of play with these values and add your own things and kind of get this to do whatever you want it to do. And that's pretty cool. There's lots of ways we could optimize this and make it so it didn't lag with only 100. We could get much more than that. The biggest thing is we're doing a scan of every object in our scene in order to find these. And that's just really slow. So if we got rid of that, this would go much faster. And that's pretty easy to get rid of as well. We just didn't do that here. And that's mostly just like a simplicity thing because example. But hopefully this is something cool. And if you need to like simulate some weird alien life force or some swarm or something, this gives you a way to do that. You could probably do a whole bunch of fun things with this. But I thought this was cool. And it seemed like it would be a fun thing to kind of show off. So yeah, I guess that's it. So if you liked what I did and you want to see more, consider subscribing. I try to post videos as much as I can. The schedule is changing, I guess. If you use this in a project or you have other questions, consider leaving a comment and I'll get to those as soon as I can. And other than that, yeah, that's it so far. So I'll see you in the next video. So until then, see you, Internet.